My name is Savir Jain, and my project was using radio signals for positional tracking, with the idea to implement it for swarm robots. When I worked at the Louisville Automation and Robotics Research Institute at U of L over the summer, they were starting a drone swarm project. To track these drones, they had set up a system of cameras. I proposed the idea of using radio signals to track the drones. Not like GPS, but more like how if you move closer to your Wi-Fi router, you'll get a better signal. Therefore, my main goal was to use the relationship between signal strength and distance to calculate the position of an object. On top of this, I wanted to build the infrastructure for implementing this tracking system, using the Robotics Operating System framework to design a network of nodes with various tasks. And that's what I'll discuss first to give a better idea of what the system would look like. So here's the structure. A central computer controls 4 base station nodes, each equipped with a receiving antenna. These antennas connect to the network transmitted by the theoretical drones and send the signal strength data over to the computation node, where it converts signal strengths to distances and then even 2- or 3-dimensional position using trigonometry. This system was programmed mostly in Python. However, the computation node is still yet to be implemented, as I need to figure out how to do this part, which leads to the heart of the project, understanding the relationship between RSSI and distance well enough to a point where position can be calculated. I took a Wi-Fi router and with a homemade dipole antenna made a transmitting unit. A laptop was connected to this Wi-Fi router and moved to various distances to see how distance changed the RSSI value. Analyzing the data led me to an equation that fit the graph. This equation is what I would then use to approximate distances when given only an RSSI value. First, I tested just this, the ability of the equation to track the distance between the laptop and an antenna. A toast test confirmed the calculated values to be equivalent to the real ones. Second, I implemented a 2-dimensional tracking system. I set up an 8-meter by 12-meter coordinate plane and placed the transmitting antenna at different points within it. Then I moved the laptop to each of 4 corners in the plane, getting the RSSI values. With all 4 received signal strength values, I calculated the distance like before, and then a program mathematically generated regions of where the transmitting antenna possibly could be. This proved to be mostly successful, with a success rate of 72% in 11 trials. Overall, the proof of concept was a success, and the next steps are to implement the computation node into the ROS network and begin implementation of the whole system with multiple robots.